Welcome to a video that will show how to determine the unit tangent vector to a curve defined by a vector valued function. Let's start off by viewing a unit tangent vector. So what we're seeing here is a blue space curve, and this red vector here is a unit tangent vector, meaning it's a vector that's tangent to the curve at its initial point, and it points in the direction of the orientation of the curve, meaning as t increases, the unit tangent vector points in the direction the curve would be traced, as we see here. So again, this red vector is a unit tangent vector. So to determine the unit tangent vector, whether we have a plane curve defined by the vector valued function r of t, or a space curve defined by r of t, the unit tangent vector will be defined by the derivative of r of t divided by its magnitude. So we basically find the derivative of the vector valued function and then normalize it, and that'll give us the unit tangent vector valued function. And the only special condition here is that r prime of t cannot be equal to the zero vector. And we know that from a previous video that if each of the components of the derivative function is equal to 0, the curve will not be smooth at that point, and therefore we could not determine a tangent vector. Let's go and take a look at two examples, one with a plane curve and one with a space curve. When t equals 1, we want to determine the point of tangency and the unit tangent vector. We can determine the point of tangency by evaluating this vector valued function at t equals 1. So when t is equal to 1, we have the vector with components 1, 2. Remember, this is in component form, so that means the point 1, 2 would be the point of tangency. So now to determine the unit tangent vector at t equals 1, we need to first find the unit tangent vector valued function, which is equal to the derivative of r divided by its magnitude. So r prime of t is going to be 3t squared for the x component and 4t for the y component. And now we need to normalize this by dividing by its magnitude. So we'll divide by the square root of 3t squared squared plus 4t squared. Now we could just substitute t equals 1 into this and have our unit tangent vector. Let's go ahead and simplify this so we have the unit tangent vector valued function. So we're going to have the square root of 9t to the 4th plus 16t squared. Now let's go ahead and evaluate this at t equals 1. That'll give us the unit tangent vector that we're looking for. So the x component is going to be 3, the y component will be 4, and we replace t with 1 here, we're going to have the square root of 9 plus 16. Well, 9 plus 16 would be 25, and the square root of 25 would be 5. So our unit tangent vector has an x component of 3/5 and a y component of 4/5. Now remember, this is in component form where the initial point is at 0, 0. We're going to go ahead and make the initial point 1, 2, and then sketch this unit tangent vector to illustrate what we've just found. It's a little hard to see, but here's the graph of our plane curve in blue, and then right here at the point 1, 2, we have our point of tangency, and this red vector here is tangent at the point 1, 2, and it has a magnitude of 1. And again, it points in the direction in which this curve would be traced out as t increases. Let's go and take a look at another one. So notice here we have a space curve defined by a vector valued function. Let's first determine the point of tangency by evaluating this at t equals pi over 6. Let's go and sketch the reference triangle just to review. Pi over 6 would be 30 degrees. So here's the angle that would be pi over 6, and this would be 1, 2, and square root of 3. For the x component, we'll have 2 times sine of pi over 6 would be 1/2. The y component will be 4 times the cosine of pi over 6, that'd be square root 3 over 2. And for the z component, we're going to have 4 times the sine of pi over 6 squared. That's going to be 1/2 squared. So simplifying this, we'll have the vector 1, 2 square root 3, and 1/2 squared is 4, so we'll have 1 for the z component. So this is the vector with its terminal point on the curve at t equals pi over 6. The point 1, 2 square root 3, 1 would be the point of tangency. Now let's go ahead and determine the unit tangent vector valued function. So we'll find the derivative of r and then divide by the magnitude of r prime. So the derivative of 2 sine t is going to be 2 cosine t. The derivative of 4 cosine t would be negative 4 sine t. And then for the z component, we'll have to apply the chain rule. So we'll multiply by 2, that's going to be 8 times sine t times the derivative of sine, which is cosine t. Now we need to divide by the magnitude. It's going to get a little messy here. We have the square root of 2 cosine t squared plus negative 4 sine t squared plus 8 sine t cosine t squared. Let's go and simplify this. So we'll have the square root of 4 cosine squared t plus 16 sine squared t plus 64 sine squared t cosine squared t. Let's go and take this to the next slide and evaluate this when t is equal to pi over 6. So the x component is going to be 2 times cosine pi over 6. Cosine pi over 6 is going to be square root 3 over 2. So we'll have 2 times square root 3 over 2. For the y component, we'll have negative 4 times the sine of pi over 6. That will be 1/2. And then here we're going to have 8 times sine of pi over 6. That's 1/2. Cosine of pi over 6 will be square root 3 over 2. And our magnitude is going to be the square root of 4 times cosine pi over 6 squared. That will be square root 3 over 2 squared plus 16 times sine squared pi over 6. Well, pi over 6 is 1/2, so we'll have 1/2 squared. And here we're going to have 64 sine pi over 6 squared is 1/2 squared. And then we'll have square root 3 over 2 squared. Let's go ahead and simplify this. So we're going to have square root 3. Here we'll have negative 2. And here we'll have 2 square root 3. Here, square root 3 over 2 squared is 3/4. 3/4 times 4 would be 3. 1/2 squared is 1/4. 1/4 times 16 is 4. Here we're going to have 64 times 1/4 times 3/4, and that's going to give us 12. So our magnitude is going to be the square root of 19, so the x component will be square root 3 over the square root of 19. The y component will be negative 2 over the square root of 19, and the z component will be 2 square root 3 over square root of 19. Remember, this unit tangent vector is in component form, so the initial point would be at 0, 0, 0, and these would be the coordinates of the terminal point. What we're going to do now is graph this where the initial point is at the point of tangency, as we see here, so we get an idea of what that vector would look like. So here we see the space curve, and this red vector here is a unit tangent vector. So when t is equal to pi over 6, which is approximately 0.52, we found this unit tangent vector here in red. Okay, that's going to do it for this video. I hope you found these examples helpful. Thank you for watching.